So thank you everybody for coming. My name is Casey Lamb. I'm a graduate student at UC Berkeley, and today I'll tell you a little bit about how we detect black holes. So first of all, let's talk about where black holes come from. So they sound like science fiction, but they're real objects. In fact, when really heavy stars die, they produce black holes. So stars are bright because they're burning a lot of energy. And this energy creates outward pressure that keeps stars from collapsing. So when very massive stars, at least 10 times more massive than our sun, die, they run out of fuel and die because they don't have the necessary pressure to support themselves. So you can think of this like a little bit like a bouncy castle. So when the generator stops, there's no pressure to hold up the walls of the bouncy castle anymore, and it collapses. So something similar happens when a massive star runs out of fuel to power and support itself. It collapses and dies. But when the star collapses, the object it forms is so dense that nothing can escape its gravitational pull, not even light. And so if light can escape from this object because it's so dense, that means it can't be seen. And that's why we call them black holes. So black holes are produced when very heavy stars die and run out of energy to support themselves. These black holes formed from dead stars are called stellar mass black holes. So in addition to stellar mass black holes, there's another variety of black holes, and they're called supermassive black holes. As their names imply, they're very heavy. So stellar mass black holes are a few to tens of times as massive as our sun, while supermassive black holes are 1 million to 1 billion times more massive than our sun. And we think they live, a supermassive black hole lives at the center of every galaxy. So this is a picture from Hubble, and each of these is a galaxy. And we think that at the center of each of these galaxies is a supermassive black hole hiding in the center. In fact, our own Milky Way has a supermassive black hole, as we'll discuss. But black holes, by definition, can't be seen. So how do we know about them, and how can we detect them? So in this talk, I'll describe 3 different methods through which we can do this. So the first one is something that was just very recently in the news. Part of the Nobel Prize in Physics this year was awarded for the detection and confirmation of a supermassive black hole in the center of our own galaxy, the Milky Way. So over the last 20 to 30 years, 2 different research groups, one at UCLA and one in Germany, have been taking pictures of the center of our Milky Way with telescopes every year, watching the motions of the stars at our Milky Way's Galactic Center. So I'm going to play an animation made for you by the UCLA group. So all these different dots are stars. And you can see as time goes on, they're all orbiting something. They're all orbiting around this thing marked with this star. There's nothing there. It's dark. They're orbiting some unknown object here at the center. You can even see this star completes an orbit. So using these orbits, they found out that there's something that's 4 million solar masses at the center of our galaxy, 4 million times the mass of our sun. Given that the volume that it's in, the object is so dense that the only thing it could be is a black hole. So although we can't actually see anything there, we can't see the black hole itself, we can see the effect the black hole has on objects surrounding it, like the stars. It's like how you can't see wind, but by the way leaves move on a tree, you can figure out what direction the wind is blowing in. Okay, so taking pictures, though, of the center of our galaxy is really, really hard. So this is a picture of what the Galactic Center looks like when you use a really big telescope with a mere 10 meters in diameter to take a picture. So this panel here, this is a zoom in of this bigger picture. You can see it's very blurry. The scale of this zoom in here is the same as the scale of the animation I just showed you. And the scales are the same. So in this zoom in box, we should be able to see all the stars that we see here, but we don't. So the reason this image here is so blurry and you can't see any stars is that the atmosphere blurs light arriving to the telescope. It's the same reason stars twinkle at night. There's turbulence or movement in the atmosphere. And so when starlight comes through, it blurs it out. Instead of seeing points of light on the sky, you see a blur. It's like when you're trying to, if you ever look down through a stream at rocks on the bottom, the water at the top is blurring the image of the rocks at the bottom of the stream, and that makes it hard to tell where exactly the rocks are. So with such blurry images, how can we actually, take pictures of the stars at the Galactic Center and track their motion like these different research groups did? So the method is something called adaptive optics. And adaptive optics subtracts out the blurring effect of the atmosphere. So the way it works is, say you want to take a picture of something like a galaxy on the sky. And so you find a star on the sky near that galaxy. Then you observe them with your telescope at the same time. The light from the star and the galaxy are passing through the same part of the atmosphere. And so they're affected by the same kind of turbulence, and they're being blurred in the same way. But you know that the star is supposed to be a single unblurred object. So you can use a computer to figure out what the atmosphere did to mess up your picture. And so you can find a correction to undo the blurring effect of the atmosphere. And this computer controls a mirror under the telescope, which is able to be deformed by very small amounts. So the computer will apply a correction to this mirror, and this mirror will bend and deform in a very particular way such that it can undo the blurring of the atmosphere. And this way, you can subtract out the turbulence or the blurring from the atmosphere effect that it has on the thing you're trying to observe and get a sharp image. And so this is called adaptive optics. So the problem, though, with adaptive optics is that you need a bright star next to your object. You need a bright star next to the thing you want to observe so you can actually figure out what the correction is. You need the star to help you figure out what the turbulence is so you can undo the effect when you want to look at the galaxy. And there aren't always bright stars in the sky next to what you want to look at. So the solution is to make your own laser. To make your own star with a laser. So the way it works is you shine a laser up into the sky. It makes a point of light up on the sky, and it's like a fake star. So then you can look at your laser star as a guide to correct the blurring effect of the atmosphere. Okay, so this is what it looks like in action. These two telescopes here, these are the Keck telescopes in Hawaii. They each have a mirror inside 10 meters wide, used to collect light from stars. And here, these yellow things, these are sodium lasers, and they're both shooting up towards here. This is the Galactic Center, taking observations. And the observations that they take are used to make those animations I showed you in the first slide. So remember, this is a blurry picture I just showed you a while ago, taken without adaptive optics, so no correction for the blurring of the atmosphere. But when you include adaptive optics using those lasers to help you correct for the turbulence, this is what you get. So you can see how much clearer this image is than this one. And in the zoom in panel, you can now see the individual stars. And this is the technology that enables us to actually see the individual stars at the Galactic Center, determine individual orbits precisely enough to figure out that there's a 4 million solar mass black hole in the center of our galaxy. So this is method number 1. I think I'll pause here and take any questions. Or Hannah, are there any questions in the chat?
Hey, Casey. Thanks for presenting so far. We do have a couple of questions in the chat. I'll pull some now. There are quite a few. A lot are general about black holes, and we'll leave those for later. First, one of our attendees would like to know, if we go on a planet with no atmosphere, will we be able to take a clearer picture? And I'll add to that, what are some complications of getting to such a place?
Yeah, so indeed, if there was no atmosphere, then there wouldn't be turbulence to get in the way of these observations. So yeah, if our planet had no atmosphere, then we wouldn't need adaptive optics. The problem with going to another planet without an atmosphere is that even the closest planets to us, like Mars and Venus, are really far away and really hard to get to. So we'd have to also build a telescope there. And that's currently not possible. But if we could find a planet without an atmosphere just for astronomy, that would be cool.
Awesome, thank you. And another attendee asks, I heard that black holes evaporate. Before they disappear, how small could they get? And can we detect such a small black hole passing through our solar system and heading toward the Earth?
So I think this might be a reference to something called Hawking radiation. So the idea is that black holes can evaporate, but for black holes to evaporate, to have already evaporated, they would have to be really, really small. So the black hole in the center of our Milky Way is 4 million times the mass of our sun. The black holes that will evaporate will be a lot smaller than the mass of our sun. So don't think we wouldn't be able to detect them this way.
Great, thank you, Casey. We'll take the other questions at the next pause. Thanks, everybody.
Okay, great. Thanks for the questions and thanks, Hannah. So, all right, so that's method number one to detect black holes. Look at how things around them are moving like stars. So that tells us about the supermassive black hole in our Milky Way. And we think actually that in the centers of all galaxies is a supermassive black hole at the center. This picture here is a picture of a galaxy called M87, and it's the one here in the center. In the center of this galaxy is a black hole 1,000 times the mass of the Milky Way black hole. And the black hole in the M87, this galaxy, has something called an accretion disk surrounding it. It's a disk of hot gas that's rotating around the black hole. And one way we can learn about M87, this black hole, is by looking at the accretion disk, this disk of hot rotating gas around it. So the black hole at the center of M87 can bend the path of light rays that move close to it. So one of the predictions of Einstein's theory of general relativity is that space and time are mixed up together, and things like black holes, which have really strong gravitational fields, can bend and warp that space-time. So light usually travels in straight lines, so maybe like my mouse cursor like that. But if the gravitational field is very strong, like right next to this very massive object, then its light will get bent and deflected. So instead of moving in a straight line like that, it'll go around and be bent. So in fact, this is what's going to happen to the light in that hot accretion disk, the disk of hot glowing gas around the black hole. So that picture I showed you earlier, that's not what you would actually see an accretion disk around a black hole would look like. This is more like what you would see. And that's because here, you're taking into account the fact that the black hole is bending the light around, it's bending the light of the disk around. You can see that it's not symmetrical, it's brighter here on this side. And that's because the light is moving around the black hole and it's coming towards us, it's looking brighter. And you can see these other rings and this dark hole here in the center. And this dark center here, that's what we call the shadow of the black hole. And so you can detect this shadow of a black hole and this lopsided brightness pattern. That's evidence that you have a black hole because there's not really anything else that could produce such a shape. However, in M87, the galaxy where this black hole lives, is so far away that even adaptive optics wouldn't be able to help us take this picture because it'd be so small we couldn't see it. We wouldn't be able to resolve such an image. So the way to get around this is to make a really big telescope by combining the information from a bunch of separate telescopes. And this is what a group of scientists called the Event Horizon Telescope Collaboration did in 2017. So each point here on this map and each name is an observatory, a different observatory used by the Event Horizon Telescope team, and they're all over the world. So these observatories are a little bit different than what you might have imagined if you've ever, say, been to Lick Observatory or Griffith Observatory in California. Instead of a telescope dome with a big mirror inside, at each site is a set or a radio dish like this. Radio waves are a form of light, and even though we can't see radio waves with our eyes, the accretion disk around this black hole will emit light in the form of radio waves, and they can be detected with these radio dish telescopes. So remember, M87, this galaxy, is really far away. And so each telescope by itself isn't going to be able to resolve the image of the black hole shadow. It's just too small to see. So the trick is to take all these telescopes at the same time to observe the black hole in M87. And so if all the radio dishes at each site individually are observing the same thing at the same time, they effectively can form one giant radio dish the size of the Earth. And then all the observations can be combined and processed together to act as a single telescope. The process of how you actually combine this information all together is really complicated, and we don't have time to talk about it today, but it involves a lot of image reconstruction algorithms to basically help fill in the gaps in information because the telescope isn't actually as big as the Earth. You just have scattered parts all over the Earth. But with a telescope like this, that effectively is the size of the Earth, by combining all these different observatories, we can resolve the black hole in M87, even though it's so far away. And so this is what the picture that the Event Horizon Telescope collaboration found. And you can see here, you can see the lopsided glow. It's brighter down here than here. And you can see that black hole shadow here in the middle. So we do know indeed that M87 has a black hole in the center, and by measuring the size of this black circle, the black hole shadow, you can figure out the mass of the black hole. So that's method 2 to figure out, that's another way to detect black holes. You can combine the information from a bunch of radio telescopes all over the world to make an Earth-sized telescope, and that helps you see a black hole shadow. So happy to take some questions here too. Are there any in the chat, Hannah?
Hey, yes, the chat and the Q&A are super active. So let's get some of the top questions. How big was the biggest black hole we've detected so far? And what was the manner of detection?
So the biggest mass black hole, I believe it's several, it's also billions of solar masses. I don't remember the name of the galaxy that's found in, but it was detected with, in a way where you measure you take a picture of a galaxy and you measure how fast the stars in the center of the galaxy are moving. And so that way you can have an idea. You can't measure each star individually, but you can see how fast several of them are moving. And by that, you can put a constraint on how massive something in the center of that galaxy is. And so that's a way you can measure black hole masses looking at light, even if you can't resolve each individual star.
Awesome. We also have a lot of questions about how black holes form and what distinguishes a supermassive black hole from a regular black hole. Could you speak to that a little bit?
Yeah, definitely. So regular black holes, we'll call them stellar mass black holes. Those are the ones that form when massive stars collapse. And those are defined to be stellar mass black holes around, say, 3 to 60, 70 solar masses, although the next thing I'll talk about has been pushing that upper mass limit higher and higher. Supermassive black holes are between millions and billions of solar masses. And actually how they form is still an open research question. We don't know how they got so big. So some ideas are maybe a bunch of smaller, like stellar mass black holes merged together and kept merging until they grew really big, or the initially a stellar mass black hole just ate a lot of material and just grew bigger and bigger, or maybe a really, really massive star at the beginning from the early universe, like thousands of solar masses, collapsed to form a very large black hole. But the formation of supermassive black holes is still a really active area of research.
And we have a technical question. Let's do one more. What is the frequency range for the Event Horizon Telescope?
Yeah, so it's radio wave frequency. And so that means when we do this, make this picture, you wouldn't actually be able to see the light from the telescope because it's in radio, at radio frequencies. But you can basically make a mapping of how intense the radio signal is And so more intense is shown as a brighter color here.
Great. Actually, there is one more question that's really relevant to something that you just said. So we'll take this one and then we'll move on. Casey, you said that the M87 black hole is 1,000 times the Milky Way's black hole, size of the Milky Way black hole Sagittarius A. And the attendee says, I think the Milky Way black hole is more than 1,000 times closer to Earth. So why didn't astronomers image that one first? In other words, why is it easier to see something outside of our own galaxy than something inside of our own galaxy? And after you answer this question, please return to the flow of your presentation. Thanks.
Okay, great. Yeah, it's a great question. So it's because how the ability to resolve something is both dependent on its size and its distance. So actually, it's a funny coincidence. The black hole in M87 is about 1,000 times more massive, but it's also 1,000 times more far away. And so that means actually when you look on the sky and see how big it is, they're about the same size. And so they're actually of similar difficulty to take pictures of. But the reason the Event Horizon collaboration did M87 first, one of the reasons is that since the black hole is more massive, this causes the accretion disk around it to vary on a slower time scale. And so that makes it part of it easier to image. But I know that the Event Horizon telescope, they are intending to also take pictures of Sagittarius A star, the black hole in the center of our galaxy. And yeah, so that's definitely a research to look out for in the future. I know they had an observing run to start that this year, but because of COVID-19, the observatories had to close, but this is definitely something that they're planning to do. Okay, so I'll talk about now the last method to detect black holes. And this is black holes interacting with space-time itself. So remember, one of the predictions of Einstein's theory of general relativity is that space and time are mixed up, and things like black holes, which have very strong gravitational fields, can bend and warp that space-time. And one of the ways this can happen really dramatically is when two black holes merge together to form a bigger black hole, producing something called gravitational waves. So here's an animation of that. So those two black spheres in the center, those are black holes. And as they rotate around each other, they're about to collide and merge. We can see all these waves coming out. Those things are gravitational waves, and that's the space-time being warped. And after they merge, you can see the waves spread out and then die away. And so by detecting those gravitational waves, those ripples, we can measure the stretching and deforming of space-time. And that's one way to detect black holes when they merge together. And this was done, in fact, for the first time in 2015 by the LIGO collaboration. And the way they did it was they had two observatories, one in Washington State called the Hanford Observatory, one in Louisiana called the Livingston Observatory. And they both measure the same signal, the signal of the stretching and squeezing of space-time. That's what's shown here on the right. This is time, and this strain, that's the measure of the stretching and the squeezing. So the fact that the two detectors saw the same thing confirmed the detection. But how do you actually measure space-time stretching and squeezing? So you need a very special type of observatory. This is not like a traditional telescope with a dome or even a radio dish. This is a gravitational wave observatory. And it's shaped like an L. So this is the center part of the observatory. This is one arm that's 2.5 miles long, and another arm here, 2.5 miles long. So it's a big L. And this type of observatory, it's called an interferometer. And interferometer comes from the word interference, which is the technique that allows us to measure gravitational waves. So the way interference works is it's what happens when you add two waves together. So a wave has peaks, which is the high part, and troughs, which are the low part. As you can think about it, if you throw a rock into a pond, there's high parts of the wave and low parts of the wave. So if you add two waves up such that the peaks match and the troughs match, you end up with a bigger wave with even higher peaks and lower troughs. So this is called constructive interference. But if you add two waves and the peaks and the troughs align, the wave, when you add them together, will cancel out and you get something called destructive interference. So you can see this, for example, if you threw two pebbles into a pond, around each pebble, the waves would spread out. And when they merge together, you'd get this funny pattern here, places where the waves are higher, some where the waves crests are lower. And that's the combinations of constructive and destructive interference. And I'll show you in a moment why this is important to interferometers to precisely measure gravitational wave signals. So I'm going to play this animation and I'll start explaining a few seconds in. So this is just first to see what's happening. Okay. So first you have this laser here and it's shooting a laser down the middle. There's a beam splitter. It splits the laser beam in half. At each end is a mirror. And so the mirror reflects the light off, and then it gets recombined back through this beam splitter and then onto a detector. And so the mirrors have been placed such that if they're perfectly still, there should be destructive interference. So there's no light here. But if, for example, you have gravitational waves, remember that wave structure that happened when those black holes were orbiting each other, the distances will change because space-time is getting stretched and squeezed. And so you'll get the interference will become constructive and you'll get a signal here. And so the constructive interference will let light through. And as those mirrors move back and forth again, show it one more time. This is now pretend space-time is stretching and squeezing. You'll get a signal here, glowing faint, glowing faint. And that is what lets you measure the gravitational wave, because if the distances to the mirrors are changing, that means that space is being stretched and squeezed. And that's how you can measure distances really precisely. The precision of the gravitational wave observatory, LIGO, is you can measure distances to the precision of 1,000th the size of a proton. So just to remind you again, this is what the observatory looks like. This was where the laser gets shot and the beam splitter, and the mirrors are at the end 2.5 miles away. And so with this observatory, scientists are able to detect the stretching and squeezing of space-time, and they discovered black holes merging. So that's the third way to find black holes. Use a ginormous interferometer to measure the deforming of space-time caused by merging black holes. So that's the end of the talk. I hope that these aren't the only methods, though, to detect black holes. There's a lot of other ones that didn't have time to talk about today, but I hope this gives you a sense of the variety of the ways black holes can be detected, and that a lot of really complicated but amazing technology is used to make these discoveries. So thanks for listening.
Thanks so much, Casey. There's an active chat Q&A box. I'm going to try to sort the questions from most technical to big picture. And we have just a few moments left for questions. First, is the light bending around a black hole similar to the distortion from the atmosphere?
It's a little bit different. So the atmosphere is blurring the light, while the black hole is actually bending space-time. It's distorting the path itself. So in one, the light is, but in both cases, the light is appearing in a different position than if it was traveling in a straight line. So in that way, they are similar.
Okay, sorry, keep appearing. Where do you direct the waves from the interferometer?
So that's, you don't actually get to choose the direction the waves come in. So the interferometer is built into the ground, so it's stuck that way. And so the fact that there's two observatories helps you, helps constrain which way the wave is coming and figure out which direction it's coming from. I only talked about the two in the United States in Washington and in Louisiana, but they're building other gravitational wave observatories around the world. There's one in Europe, they're building one in India, and they're building one in Japan also.
We have time for exactly one more question. Are black holes similar to the Bermuda Triangle?
And that things disappear. I guess if you sent something into a black hole, you wouldn't see it again. And if you sent something into the Bermuda Triangle, you wouldn't see it again. So maybe they are more similar than one might think.
Awesome. There are some further questions, but we're out of time. You are welcome to try to see them on the webinar after the fact, and many of them that are repeated and are getting repeated in the chat, I actually answered through the Q&A box. So thank you so much for joining us, and the recording should go up on the website in the next couple of days. Tech's a little overwhelmed. So thanks for your patience and for coming. And thank you, Casey, for this great talk.
Thank you. Thanks all for coming. Thanks for moderating.